Today, we're going to peek under the hood of the software that powers everything from air traffic control to the GPS in your car. It's a really clever system, and it's designed to solve one of the toughest problems in tracking.
So let's just dive right in with the big question. Imagine you're trying to predict the exact path of a fighter jet or a swerving car or even just a bird. Simple, straight-line predictions, they just fail when things get unpredictable. So how do modern tracking systems actually keep up?
You see, the real heart of the problem for any tracking system is knowing where a target is going to be in the next moment. It's called state estimation. And for systems where reliability is everything, we're talking aviation, autonomous driving, getting that prediction right is absolutely critical.
So the traditional way to do this is with a single predictive model, something like a common filter. And look, it's great if your target behaves itself, flies in a perfect straight line at a steady speed. But the second that target does something interesting, like a sudden turn or slamming on the brakes, that single rigid model, it just starts to generate huge errors. It can't keep up with what's actually happening. Think about it this way. A model that's built to track a car on a long, straight highway, it's going to be perfect for that one job. But if you take that exact same model and try to use it on a sharp, winding off-ramp, it's going to be hopelessly lost. The physics have completely changed, but the model hasn't, and your prediction is going to be terrible.
So, if one model just can't handle all the possibilities, what's the answer? Well, what if, instead of relying on a single, overworked generalist, we built a team of specialists? A team where each one is an expert in just one specific type of movement.
And that brings us to our team. All right, first up, let's meet the straight-line expert. This guy is based on the constant velocity model, or CV, and research shows it's the absolute best for simple, non-maneuvering targets. This is your expert for that long, boring stretch of highway.
Then you've got the accelerator. Now this one, based on the constant acceleration, or CA model, its specialty is predicting linear motion, things speeding up or slowing down. It's the perfect model for, say, a drag racer blasting off the starting line.
And rounding out our team is the turner. Based on what's called the coordinated turn model, its one and only job is to handle smooth, constant speed turns, which, remember, is exactly where the other models fail. So for a jet circling a point in the sky, this expert is right in its element.
Okay, so we've got our dream team of specialists. But a team of experts is pretty useless without a great manager, right? Someone who knows who to listen to and when. In this system, that manager has a name. It's the Interacting Multiple Model Algorithm, or IMM for short.
Now, the real magic of the IMM isn't just picking one expert and telling the others to be quiet. No, it's about intelligently listening to all of them, all at once. It weighs and blends their individual predictions to create a single forecast that's way more accurate than any single one of them could ever be on its own.
And it all works in this really neat continuous loop. First, you have the huddle, where the experts all share information to kind of adjust their own starting points. Next comes the scorecard. Each expert makes his prediction, and the manager scores it against the latest real-world data. And finally, the final call, where the manager creates a single weighted prediction, giving the most influence to whoever had the highest score. And this cycle just repeats, over and over, constantly adapting.
All right, so that all sounds great in theory. But does this team of experts approach actually work when the rubber meets the road? Let's take a look at the data from a really challenging test.
So the test scenario involves tracking a target that's pulling a sustained, high-speed 5.6 G turn. This is a seriously tough maneuver, and it's basically designed to make a simple model completely fall apart. So how did a single expert do against our expert team?
Well, the results are pretty stark. The single straight-line expert had a peak position error of 107 meters. It was way, way off. But the IMM expert team, the one with our turning specialist, its peak error was just 65 meters. That is a massive improvement in accuracy, and it happens right when it matters the most.
And this chart, this is the beautiful part. It shows you exactly how it works. As the target starts to enter that turn, the IMM manager sees that the straight-line expert's predictions are getting worse and worse, while the turner expert is just nailing it. So it dynamically shifts its trust. It basically says, "Okay, Turner, you're up, you take the lead." The team adapts on the fly. It's brilliant.
So this is clearly a powerful system. But if you were building one of these from scratch, what's the single most important decision you have to make sure it actually works well?
You might think it's all about the super complex math or fine-tuning the parameters,
But the research gives a surprisingly clear answer. As the author Anthony Genovese puts it right in his conclusion, the biggest factor for success, it's all about who you pick for your team.
And this is so critical. The research shows that you could spend forever tweaking all the internal settings, the little probabilities of switching between the models, but those changes actually have a pretty small impact on performance. What really moves the needle is making sure you have the right experts on your team in the first place. For tracking a plane, that means having models for straight flight, for acceleration, and for turns. Having the right team is way more important than having the perfect rulebook.
And that really is the beautiful elegance of the interacting multiple model algorithm. It isn't one giant, impossibly complex model trying to do everything. It's a smart manager that creates a single, incredibly robust and hyper-accurate forecast by just combining the wisdom of a team of simple, focused specialists.
It's an amazing solution for a single, unpredictable target, which kind of leaves us with one final big thought. If it takes a whole team of models to track just one complex object, what on earth happens when you need to track a whole team of objects, all interacting with each other? Now that's a puzzle for another day.